All right, this lecture is to replace the lecture that we would have had given the fire drill, and I'll make two short videos that should get you caught up, and then the next class period we will spend working example problems. So this is a brief review. This slide is a brief review of what we did in class last time, talking about mutual inductance. So first of all, mutual inductance means that we have two inductors in they're coupled because they share some flux, so the flux that one inductor produces is seen by the other inductor, and this can have implications inside circuits. One of the implications is two circuits that are otherwise not physically connected can be connected through inductive coupling. One example of inductive kind of coupling is many of you probably have the systems where you can take your cell phone and just lay it on a surface that's designed to charge the cell phone without plugging the cell phone in. That's an inductively coupled kind of circuit. An analogous phenomena also occurs with capacitive coupling, but it's not as common. And usually we only have a problem with capacitive coupling where we have circuits that either involve very high speeds or frequencies, or we have very large voltages and fields. Another example would be if the physical dimensions of the circuit are very large. So in other words, if you have a lot of really large bus work separated by other bus work by distances that are fairly small. So big equipment in a small space, that can induce capacitive coupling as well. But it's not seen as often, and we won't discuss it in this course. Mutual inductance, well, I mean, it's seen, but it's not a problem. So mutual inductance means that a change in magnetic flux in one coil induces a voltage in the coupled coil. This is also the basis for how a transformer works. The polarity of the induced voltage depends on the physical winding directions of both coils and the direction of the current and voltage that are defined in each coil. So it would be very difficult to represent schematically the direction of the coil winding. That requires pretty good, artistic skill, and even then is easily open to misinterpretation. So one of the things that is done in electrical engineering that's very different from physics is we use a convention to define the direction of the winding, referred to as the dot convention. Now, once you learn the rules on the dot convention, you actually don't have to worry about the winding direction because the dots take care of that. So here's just a simple example of two coupled coils. Coil 1 has voltage V1 and current I1. Coil 2 has voltage V2 and current I2. You'll note here the two dots. And you'll note that there is some flux that is linking the two coils. So what the dots tell us is, for example, we know that since I have a current in coil 1 and there is some shared flux, that current in coil 1 will induce a voltage above and beyond this voltage that would be applied to coil 2. It'll induce a voltage in coil 2, and the induced voltage is proportional to the mutual inductance and the time derivative of the current in the first coil. Now the direction is what's in question. So the dot convention applies as follows. If a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage on the second coil is positive at the dotted terminal of the second coil. The same can be said if a current leaves the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is negative at the dotted terminal of the second coil. So if we look at an illustration of just some different possibilities, here's an example where we have a current I1 applied to this coil shown in figure A. You'll notice it is entering the dot, which means that the induced voltage in coil 2 is positive at the dot, so hence the plus and minus signs. Now notice here there is no source connected to coil 2, and that's obvious that coil 2 is just open circuited because there's no current shown here. So right now we're just talking about the polarity and direction of an induced voltage. And that voltage is equal to M, the mutual inductance, times di1 dt. So two things to note. First of all, the voltage when the current I1 enters its dot, the voltage at the other dot is positive. The voltage is the mutual inductance, and then the time derivative on the current is the current in the other coil. And so that's consistent here. So let's look at figure B. In figure B, the current is entering the dot here. Now I have a little bit of an issue with the book's labeling, because basically what they've done is they've labeled the voltage in figure B in the same way as they did in figure A, but you'll notice there is a negative sign. I probably wouldn't do that. I would probably put the negative sign at the top and the positive sign at the bottom and make this sign positive, but as you know, it is exactly the same thing. So what makes figure A positive and figure B negative is that in figure A, the current I1 is entering the dot, and the dot is at the top on coil 2. In figure B, the current I1 is entering the dot, and the dot is at the bottom of coil 2. So this is still going to be positive at the dot because this current is still entering. Once again, I will say, the one issue I have with this figure in this textbook is if I were doing it, I would probably put the positive sign here by the dot and the negative sign at the top, and I would make this sign in the equation positive. So I'll let you look at the other possibilities. Here, the current is leaving the dot. So when the current leaves the dot, and let's look at D because that doesn't have that sign ambiguity. Here I2 is leaving the dot, so that means the voltage that it induces in coil 1 is going to be negative at the dot, which you can clearly see here. This voltage is positive at the other end and it's negative at the dot. Now this is going to become more clear, when we work more example problems, I'm going to show an example problem on the video, but we'll actually rework it in class. All right, so when we apply this to circuits, basically we have to take into account, when we write our KVL equations, we have to take into account that there is an induced voltage due to the mutual inductance in the system. And so what that's going to do is that's going to introduce some additional terms into the mesh equations. So we use the dot convention to determine whether the voltage polarity of that additional term is going to be positive or negative as we go around our mesh. To solve a coupled inductor problem, you've got to know a couple of things. You've got to know where are the dots, and then you've also got to know what are the values of the inductances and the value of the mutual inductance. In this class, one of the things we'll look at will be AC transformers. As a general rule, for what we're looking at in this class, when we talk about inductive coupling, we're going to be talking about strictly AC circuits and single frequency AC, at least for now. So for L, we're going to use j omega L, and for M, we'll use j omega M. So the examples that we're going to work here, if they haven't already been converted to the phasor domain, we'll convert them to the phasor domain. All right, one last thing to talk about is the series enhancing and series aiding and series opposing connections. So basically in figure A here, these two inductors L1 and L2 physically are wound in the same direction. So the dot on both of these is at the top. So if you were to write a little KVL equation along this string here of inductors, and just look then at what is the inductance. Basically in this first figure, because the dots are on the same side, you'll have L1 plus L2 plus 2 times M. So you get a voltage drop across L1 due to the fact that you would have a j omega L1. You get a voltage drop across L2 because you would have a j omega L2. But then you also will have the mutual term of L2 affecting L1 and of L1 affecting L2. So what this is saying is if these two inductors are placed in series, that basically the overall equivalent inductance will increase, and it'll increase by a value of 2 times the mutual inductance. If you look at the right hand, the figure on the right hand side, you'll notice the dots are on opposite ends of this series connection. So what's going to happen then is, because of the direction, remember when this current enters this dot, the induced voltage over here is positive on the dot side and negative here. So given that current is flowing from left to right, the main voltage drop, I times j omega L, will be plus minus, and the mutually induced voltages are going to be in the opposite direction. So what happens then is the inductance actually decreases, the total inductance decreases by this value 2M. So L is L1 plus L2 minus 2M. Now, if we look at the total stored energy, basically the total stored energy in an inductor, as you probably remember from circuits 1, is 1/2 L1 I1 squared. In inductor 2, it's 1/2 L2 I2 squared. In the mutual inductance, the 1/2 term will cancel the 2 here. And so because one of the induced currents is due to I1 and one is due to I2 in a typical problem, then we'll have M I1 I2. Now in this figure, I1 and I2 are equal because everything's in series, but the general form of stored energy is this form right here. Likewise, if the inductors are a series opposing type connection, then the total stored energy actually will decrease by M I1 I2. So one problem to ask is, one of the things that we've talked about is sometimes, especially in power distribution systems, you build up an excess of inductance in your system because you have long transmission line runs. And so the question is, could you, in a system like that, maybe at the end of the long transmission line, put an inductor that is wound in such a way that you have a series opposing connection, and would that then have the effect of quote unquote canceling out the inductance in the transmission line? And the answer is theoretically yes, you could think about doing something like that, but in practicality, no, because inductors are something that there's only a certain range of order of magnitude where it's reasonable to build one. And also, those voltage transmission lines are very high voltage as a general rule. So you've got issues with winding an inductor so that you don't get breakdown among the coils. So really, those inductive kind of filters built for that purpose. The other thing is, remember that you have to share flux. And so if you have power distributed across a long geographical region, then any inductive kind of filter that you would put at the end of that long transmission line, it would not couple all of the flux. So you wouldn't have the effect then of that inductor canceling out the power transmission, the inductance of the power transmission line. So that won't work for that circumstance. That would only work if you had some local stray inductance and you wanted to try to get rid of that. Sometimes, just depending on the physical configuration, especially if it's a wound inductor, then you can do some things to optimize coupling the flux and wind something in an opposite way. But usually, just from a practical point of view, inductance that you don't want is typically not due to a nicely wound coil. So as a general rule, that would not really work. Okay, the last thing I want to define in this lecture is the coupling coefficient. So if we come back here, you can use an energy argument or you can just use a linear argument. So if we look at this equation on the series opposing connection, and actually, let's look at it from an energy standpoint. You can't have negative energy. So the lowest W that you could possibly have would be when W is equal to 0. That's going to put a condition on the relative values of M, L1, and L2. If you work through the math, what you find out is that the mutual inductance can't be greater than the geometric mean of the two coupled inductors. So M is always going to be less than or equal to L1 and L2. Which leads us to defining something called a coupling coefficient. If the mutual inductance is the maximum that it can possibly be, what that means is 100% of the flux in coil 1 is coupled to coil 2. And so in that case, M would be equal to the square root of L1, L2, or the geometric mean between the two coupled inductors. So we define something to give us an idea of how close to perfect is our coupling, known as the coupling coefficient. So one way to look at that is that we have this constant K in that equation. So M is K times square root of L1, L2. And if K is equal to 1, then we have perfect coupling. If K is equal to 0, we have zero coupling. So K is a number that's going to range from 0 to 1, giving us a minimum and a maximum mutual inductance that we can have. Coupling coefficients are commonly given as a rating or a specification in things that you might buy, like a transformer. They will often tell you what the coupling coefficient is, and that's typically something that they measure when they spec out their product. So another way to think of the coupling coefficient is if we have two coils, coil number 1, which has total flux of phi1, and if phi12 is the flux that's shared between coil 1 and coil 2, then basically K is a ratio between the flux that gets shared and the flux that is confined only to coil 1. And we can reverse that and look at it from a coil 2 perspective. K will be the same because the coupling coefficient is a geometric factor. So you can enhance, in air, you can enhance the coupling coefficient by adding magnetic materials and by really optimizing your geometry and minimizing your leakage. So there are some ways you can maximize K, but in theory you will never reach 1. So K, that would be a perfect case, and there's always going to be leakage and other issues that will take away part of your coupling. But K can be very, very high. All right, so that concludes the part of kind of catching you up on the theory of inductive coupling and the coupling coefficient. And then I want to do one quick video illustrating one example.